Well, hello and welcome back to PC Retro Tech. It's actually been a while since I've made a video on the channel, and regular viewers will know that's because I've just been moving house to Cambridge here in the UK. And I put an unlisted video in the community section, which many of you will have got notifications about, just explaining what went wrong and a little bit of a cautionary tale for those who might have moderate-sized PC collections like myself. It's really quite the logistical challenge to move that stuff about. But anyway, this week I want to get back to the IBM 8514/A standard and this ATI video card, which actually supports it perfectly. So this is a video standard that was released by IBM at the same time as VGA, but it has a graphics coprocessor and is able to do some things like filling polygons and blitting and so on. So we started off just looking at the IBM adapter interface, which is a software interface that sits on top of the hardware. And because the ATI card with the Mark 8 chip is 100% register compatible with the original IBM 8514/A, this adapter interface software from IBM works perfectly with this card. So we checked it out, but we found it was very, very slow. And so the only way that we can go forward is to actually program the card at the register level instead. So I found some documentation for the Mark 32 chip from ATI, which is very similar to the Mark 8, and started to check out some of the features. We got the Bresenham line drawing algorithm working, and we got the polygon fill working just fine. But when it came to the blitter, we were just getting filled rectangles, regardless of what it was that we were blitting. So blitting just means to copy an image from one place to another, essentially. And this was a little bit puzzling, but I've since made some progress on that, and so that's what we're going to take a look at in today's video. Previously, if I drew a triangle and filled it, and then blitted it to the right-hand side, I just get a rectangle that's filled on the right-hand side. And now it actually just copies the triangle, which is what we want. Now the problem turned out to be a typo in the ATI manual. It had one of the registers recorded incorrectly, and it's understandable how this happened. So there's a specific ATI mode where the registers are handled a little bit differently, and I guess they just copied the wrong information for the IBM specific mode. And of course, I'm just using the IBM 8514/A compatible mode. Anyway, I also had a typo around about the same point in my program, and that made the whole problem really difficult to detect. But now it's working, or rather, it is copying a rectangle over. You can see it doesn't just copy the triangle, but an entire rectangle of pixels. And so if they're black on the left, it'll just overwrite whatever's on the right with black pixels. So that's maybe not exactly what we'd like. We'd like it to just copy the triangle. What we have at the moment is called a color source split. It just copies the exact color of the pixels in a rectangle on the left to the right-hand side. But you can do something called a mono source split, which will actually look and see whether or not a pixel is filled in or not on the left. If it is, it will use a foreground color on the right, and if it's not, it will use a background color. And of course you can set it up so that that background color is just the color of the existing pixel on the right hand side so that nothing changes. So what that would do is if you had a black pixel on the left, nothing would change on the right, and otherwise the pixel would be copied over. So that's what I want to get working next, and unfortunately I haven't been able to get it to work so far, but hopefully it's just something simple. Anyway, in the meantime, let's see how fast this blitter will actually run if we let it go at full speed. And yeah, it seems to be pretty good actually. Well, I was just about to give up on this blitter, and then I had one final idea, and at last I actually got it to work. I mean, bear in mind that a lot of the documentation that's out there is on the IBM adapter interface and not the register level programming. And the ATI documentation is really vague. But now it's actually copying just the triangle over, which is what I wanted. But it actually doesn't work anything like what I thought. And I'll explain in a moment exactly how it does work. But first, I thought it would be interesting, now that we've got it working, to actually time the thing. So I'm going to draw 10,000 triangles, and fill them and then blit them over. And I actually did this earlier, and it took 25 seconds to draw the triangles and to fill them in, and it was another 25 seconds to blit them. So it's interesting that the time for the blit is about the same as the time for the fill. And I guess this is just down to the speed of video memory. But if we were going to use this for, say, 3D object rotation, we probably wouldn't have an object this large. So I think what I should do now is try some much smaller triangles and see how many of those I can blit in a single frame. And that'll give an idea of whether we can do smooth animation or not. Before I do any 3D rotation, I thought it would be good to describe what I know about the architecture so far. And I think some of you guys are going to be really interested in this. It's absolutely fascinating. Obviously, it's writing pixels into video RAM, and this is happening at the output here. And it's based on a computation done by an arithmetic logic unit here, and that's based on a bunch of inputs which are all over on the left here. And this is what I thought would be sufficient, but as you can see, there's lots of other moving parts here. For example, the input has a mono source and a color source, and these are used in a really intriguing way. The color source allows you to specify a foreground color and a background color, and these could just be fixed colors if you want. For example, there are two registers that you can use. I could put, say, red in the foreground color register and use that for the foreground color source, and then put black in the background color register and use that as the background source. And then the mono source is used to choose which of these two colors gets used on a pixel by pixel basis. When it outputs a 1, the foreground color gets used. When it outputs a 0, the background color gets used. So what can the mono source be? Well, you can set it to be always 1. It'll always use the foreground color. And for example, if you wanted to draw a rectangle and fill it with all the same color, that's what you do. But you can also set a pattern, and there's a couple of bytes of registers that you can put a 1-0 binary pattern in. So if you, for example, alternated 101010, it would alternate foreground, background colors as it moved across the screen. And if that's not complicated enough for you, you could also get this 1-0 pattern from system memory. It gets copied across the ISA bus. It basically just sits and waits for the 1-0 string to come from the CPU. And finally, you can also get this binary pattern from video RAM itself. And this actually is very interesting because the way it works is that there is a read mask applied to the pixels in the source image. And this read mask tells it which bit planes to ignore. So for example, I could get it to ignore the green and blue bit planes, and it would only consider the red bit plane of all the pixels in the source image to determine whether to return 1s or 0s. So you have to be a little bit careful about this because when it encounters a purple pixel, that contains red, so it's going to get a 1 here. And there's a little formula that you have to use to decide whether you're going to get a 1 or a 0 for each pixel. But at any rate, this can then be used to select between these two colors. And the color source itself can also be lots of things. As I said, it can just be fixed colors, but you can also take the color information that's going to be written across to the output from either system memory or an image in video RAM again. And there's also a fifth option here just for the foreground color, and I think this is ATI specific. You can just have a fixed color pattern that's used. And you'll get 4, 8 or 16 bits of color information per pixel from the foreground and the background source. This would depend if you were in the 16 color mode, 256 color or 65 536 color mode. And the latter's only available on ATI, of course. The IBM only had the first two options. Anyway, the way I set my blit up originally was that I used the blit source from video RAM, the source image, for my mono source. So for example, whenever there's a red pixel in my triangle, I'd get a 1 here and it would select foreground color. And for the foreground color, I also used the color of the pixel in the source image, or at least that's what I thought I was doing. And in the other case, it would use, well, I just set it up to always return black in that case. Well, that didn't actually work, and the reason is quite interesting. The blitter has a buffer in it, and that buffer can only have either mono or color information in it, not both. So I can't use the blitter source for both the mono source and the color source, which was really irritating when I discovered it. But there's an easy workaround. If I'm trying to copy a red triangle over, then basically I set this up to only recognize red, and I'll get ones or zeros from my mono source, depending on whether there's a red pixel or not. And then I just set a fixed color for the color source. Instead of using the color of the pixel from video RAM, just use the foreground color register. And for example, I just put red in that, and then it will just literally copy a red triangle over. The only problem is that it's also going to copy all the black background pixels across if I set this to black. And that's not what I want. And that's where source destination mixing comes in, which is what the ALU is for. It will combine the source color, whether it's foreground or background, depending on which one's been chosen, with the destination pixel color. And there's lots of different mixes that can be used. So there's a different function for when you're using a foreground color as the source, and there's a different function for when the background color is used for the source. So one of the options, of course, is just to copy the pixel from the source to the destination. Another option is to ignore the source and just leave the destination as it is. And that's actually what I wanted to do for my blit. But there are lots of other options. You can add the source and destination together. You can OR them, AND them, XOR them, or whatever. And that'll give you a pixel color ready to be copied into video RAM. And believe it or not, there are yet more options. You can check that color value and see whether it's greater than the destination pixel color or less than, and only copy it in if it is. So there's a destination comparison function you can use for that. And finally, one additional option is a right mask. You can actually mask off certain bit planes on the output and not touch them. So very sophisticated setup indeed, and lots of flexibility. Well, I have it drawing smaller triangles now, but I've also made another change which you can probably immediately see, and that is that the triangles just appear out of nowhere. And that's because instead of drawing the triangles on the screen, filling them on the screen, and then blitting them into position, I'm now composing the triangles in a little off-screen buffer, just out to the right here as it happens. By default, the adapter sets things up so that there's video memory allocated for 1024 pixels in the horizontal direction, even in the 644/80 mode. So you have some extra video RAM out here that you can draw things into, and then when they're ready, blit them into place. And this is how it's intended to be used. The only problem is that the adapter interface seems to set up what's called a scissor, which is like a viewport, if you like, for the exact dimensions of the screen, so 644/80, and anything outside that scissor just gets ignored. So for a long time I was just blitting black triangles onto the screen, which really isn't very much help. And once I figured out this was probably what was going on, I had a bug in my scissor code, and I was accidentally cutting off the top bit of the X coordinate. And so this just led to a completely black screen, which had me scratching my head for ages. And I was a little bit worried that maybe this Mark 8 chip doesn't support everything that's documented for the Mark 32 chip in the manual that I'm using. But it turns out this is actually a standard 8514/A feature, and everything is working just as you'd use it on that adapter. So now the triangles just seem to appear out of nowhere, which is exactly what we want, of course. Now I decided to time 10,000 of these, and it takes about 10 seconds, and this is about 1,000 a second or 15 a frame at this size. And so I think we're going to be able to rotate some small objects with this. Now you can actually make it a lot faster by turning turbo on. It'll go in about 4 or 5 seconds, so at least twice as fast. The only problem is that when I do turn turbo on, you can see that various characters get duplicated on the line below. So this I got copied down, and there's obviously a space that's been moved down here and so on. And we saw this previously, and it was actually a viewer that suggested maybe it's because when turbo is on, the bus speed is too high for the card. And indeed, if I turn turbo off, which I've just done now, and redo the directory listing, everything's perfect. So it really is that this card can't handle the higher bus speed. So I'm going to have to leave that off, which will limit us to 15 triangles per frame, but that should be enough to draw a pretty smooth rotating object, which I'm going to try and do now. Well, I seem to have got this to work, and that probably surprises me as much as it will you guys. There wasn't much debugging actually, but you'll notice that it's drawing black lines around the triangles, and this is not expected. I am using the option to omit the final pixel of each scan line and the final scan line of each triangle, but I would have thought that'd be needed to stop doubling up the lines between all the triangles. So this is a little bit of a mystery, but I like the way it looks, so I'm just going to leave it as it is. It's also flickering, and it's not the camera or the monitor. This is an LCD monitor. Instead, it's the way we're doing animation. First of all, nothing's synced with the vertical retrace, so everything happens at a random time. And in particular, we're blanking over the image between each frame before we draw the next one. And so I'm going to have to change the code so that we draw the image off screen in entirety before blitting the whole thing over, and then syncing that with vertical retrace. The adapter interface actually has an option for doing that, so it seems to be necessary for the blitter itself, so we might have to do that as well. So the other thing is this is running a little bit slower than it really can, and that's because it looks awful if you run it at full speed. It's just too fast. So I put a little delay in, which is nice. It means we've got plenty of time to play with. Now the other thing that I've done here, which I've personally never done before, is a trick that's used in the demo scene a lot to speed up rotation. If you do things the really lazy way, you'll just rotate every vertex in the object, and there are 12 vertices in an icosahedron. But this is really expensive. Lots of rotation matrices, lots of floating point arithmetic, or if you work a little bit harder, maybe lots of integer arithmetic. But instead of rotating all of the vertices, what you can do is just rotate the coordinate axes instead. So there's just 3 rotations to do per frame. And this is a lot cheaper. So basically you just take a vector in the x direction, a vector in the y direction, a vector in the z direction, and rotate those. And because every vertex of the icosahedron is just some combination of those 3, if you take that same combination of the rotated coordinate axes, you're going to get the rotated point. And so this actually saves quite a bit of arithmetic. It still works out to 9 multiplications per vertex that you want to rotate, but this can actually be made really fast if you also use a lookup table for the multiplications themselves. I actually didn't do that last step on this because the 286 is fast enough with its multiplications to not really make any difference if you do that. And I'm really impressed with the speed actually at how this came out. And now the other thing I want to do is some shading. And this is VGA, so we have hundreds of thousands of colors that we can use in the palette. So I can set the palette up so that each face is a different shade of blue. But in addition to that, I can also make it so that as a triangle turns towards the viewer, it gets lighter, as though there's a light source out in that direction. And this is actually fairly easy to do. All I need to do is compute a normal for each triangle. So this is just a perpendicular vector to the triangle, and there's formulas online for how to do that. And so if that normal or perpendicular vector faces towards the viewer, you know the triangle is face on to the viewer, and so it should have a lighter color. So if I do that, I'll get a nice shaded effect. So let's try that and see if we can get it to work. Well, to my utter shock, this is actually working. So I've made it a little bit narrower now, so it's not quite so distorted. And of course, I'm also composing the object entirely off screen before blitting it all across in one go. And this has got rid of all of the flicker that we saw previously. I didn't even need to worry about syncing with the vertical retrace. This is an LCD monitor after all, but Presumably there's still a little bit of screen tearing going on here, and if I wanted to get rid of that I would have to do the syncing. But check out that shading, it looks fantastic. So the way this is done is using an ortho-normal vector instead of a normal. So this is the same thing except it just has length 1. So if it's facing towards the viewer and it's length 1, then it'll be 1 in the Z direction. But if it's facing to the side and still length 1, then it'll be 0 in the Z direction. And of course you'll have everything in between. So you can use the Z coordinate to tell how much it's facing towards the viewer. And then you can use that to pick a color. Now, unfortunately, it looks still a little bit jerky, and that's not because of the low frame rate. That's just because we only have 16 colors. So the colors stay the same for a while and then change suddenly as it rotates. That's a little bit of a shame. There's not much I can do about that because of the adapter interface that I'm using to set everything up. So the other thing I've done is take out the little delay that we had between frames. So it's going a little bit faster now, and it's not needed anymore since we've got no flicker to get rid of. And the only thing remaining, I guess, is to turn turbo on and see how fast it runs at full speed. And yeah, that's pretty impressively fast. So yeah, you can do 3D with this 2D card. Of course, I wouldn't want to run it at this speed because of the text mode problems that we saw, but yeah, the graphics works just fine. Before I move on, there's one more thing that I want to check out, and it's what ATI calls a non-conforming blit, meaning that it doesn't conform to the 8514/A standard. It's something extra that ATI has added on, and it involves this extended ATI register. You can see here that this register is not available on the IBM 8514/A. That'd be listed here if it was. You need an ATI Mark 8 or Mark 32 chip in order to have this. And a lot of the extended registers actually are only available in the Mark 32, but this one, luckily for us, is available for our Mark 8 card. And it's bit 1 that I'm interested in, this special polygon fill mode. And when you enable it, it enables polygon fill blit mode. So it's a little bit complicated how this works, but basically if you draw a polygon on the screen, just the outline only, and then enable this mode, when you do a blit of that polygon, it will actually fill it in as it goes. So the way it works is that when it hits a colored pixel, it will interpret that as the edge of the polygon, and it'll flip some internal flag to say, okay, now we're inside the polygon. And when it reaches the other side of the polygon, where the other colored pixel will be, it'll flip that flag again and say, okay, now we're back outside the polygon again. So this actually should save us a whole load of time because the polygon fill will effectively be saved now that it's combined with the blit operation. And that's probably around about a third of the time currently. So I hope that this will actually speed things up a bit. So let's give it a try and see whether it works. Well, I managed to get it to go, but once again it was more trouble than I thought. First, you have to set the card into ATI specific mode by writing to a particular register. But that register controls the dot clock for the card, and that's to support all the different ATI video modes that IBM didn't have. So there's an appendix with all the frequencies, and I was able to sort that out. But then the register set is completely different. It's not just the same ones with a few changes like I thought. And the blit works quite differently. You can actually set the destination rectangle to be a different shape to the source. And for some odd reason, you can even set the x-coordinate of the first line of the blit to be different to the x-coordinate of all the other lines of the blit. I've no idea what that feature would be for. And in addition to that, I needed to use a color source blit here instead of a mono source blit. I don't completely understand why. And also, the blit just starts automatically once all the parameters are in. You don't actually have to issue a command to get it going. So it really is a little bit different. But as you can see, it's quite a bit faster, about 30 frames a second now, or 50% faster. And yeah, I'm really happy with this. It's no 3D card, but certainly good for rotating small 3D objects. So let's turn turbo on and see how fast it is now. And yeah, it's just a blur, so plenty of performance here. There's one more experiment that I want to do, and this was suggested by Jim Lannert. and that is whether or not this card will actually work inside a PC. Of course, it's a 16-bit ISA card, and the PC only has 8-bit ISA slots, but a lot of VGA cards work in some capacity in an 8-bit machine. So I'm going to turn it on and see whether we get a picture at all. So the machine takes a little bit of time to boot up. It probably means that I haven't selected the jumpers correctly on the main board. But let's see if it boots up anyway. Very often it will just start going. And yeah, look at that. It does actually seem to be doing something. I probably have the keyboard set up incorrectly as well at the moment. Let me go and sort this all out, and we'll see if we can actually get the code to run on the PC. So the card certainly has the ability to transfer 16 bits of data over the ISA bus, but I'm not actually using that feature, so let's see if it goes. Well, I have everything copied over, and I should have mentioned this is actually an IBM XT, not PC, but the architecture is basically the same apart from the hard drive. So let's run this, and I have to do HDI load first. This is the actual IBM driver, so let's see if that does anything. And oh, what a shame, that seems to be the end of us right there. So the actual IBM driver itself won't load on this machine. It's probably expecting a 286 or later. That's really unfortunate. So yeah, if I just run my demo, then absolutely nothing is going to happen here. Well, that was worth trying, but apparently it does actually need the full 16 bits, or there's some other incompatibility. But anyway, it was worth a try and an interesting experiment nonetheless. Well, that's going to be it for the hardware experiments for today, but there's a couple of other things that I wanted to mention before closing. So I did a little bit more reading on the chips themselves, and it turns out there are another two that are actually register level compatible with the IBM 8514/A. So there's the Chips and Technology 82C480 chip, and also the Western Digital WD9500. So if you have video cards based on either of those, then more than likely it actually supports everything. There were other cards that had the higher level adapter interface compatibility, but not the register level. So this would include the Sanglabs cards, for example. And you needed special drivers for those, like the IBM driver, but designed for those specific cards. And ironically enough, this actually includes IBM's own XGA. It is not register level compatible with the 8514/A. It only supported it at the adapter interface level. So I thought that was an interesting piece of trivia, and probably puts to rest some of the misinformation that's floating around out there about these chips. Anyway, tell me what you think. Would you have used this for 3D games if it had been cheap enough back in the day? It's really not cheap enough now, to be honest. Or would you have just waited until proper 3D accelerators came along? Anyway, that's it for today. Thanks very much for watching, and we'll see you in the next video. Bye.